Presentation 12. Today's presentation we're going to deal with the universal synchronous, asynchronous receiver transmitter, the USART. As usual, I like to start by showing our architecture. The items in green are the ones that I've already presented, and today we're going to talk about the USART. That's in layer 2. Now the agenda for today will be, I'm going to give you a little bit of background, then we're going to develop the framework, and finally we'll go through a couple of examples. Now let's start with an example. Here we want to communicate a ATMEGA 328 with a laptop serially. To enable that, we use a USB serial adapter. Now on the laptop, we would have to install a Terra terminal. Next, we would open that application. Now before we can communicate, the laptop can communicate with the microcontroller, we need to do some setup. So first we would have to configure the terminal, and there are a couple of parameters. One is the new line. So after a new line we could add a line feed or carriage return. In this case they've decided the carriage return for the receiving and for the transmitter. But in general, that's one parameter that we have to look at, because some sensors have certain requirements with respect to with the new line. Next, we would always use the BTF-8, that's the ASCII. So those are the parameters that we have to consider when we talk about the terminal. Next, with respect to the serial, we will need to set up the speed, bits per second, that we're going to be transmitting, the data frame, how many bits. In this case I'm showing 8. Then the parity, which we would have the option for doing add parity, even parity, or no parity. And finally we have here the stop bit. In this case they show 1, but we could use 2 also. Now the reason I'm showing you all this is because when we set up our microcontroller, these are the parameters that we have to configure. So with this example, that gives you an idea of what needs to be done. Also, if we want to have communication between the microcontroller and the laptop or microcontroller or any sensors, all these parameters, they must match. So let's look at the microcontroller specifically. So the read parameter is called the RDX, and it's associated with port D0, which is pin 2. The transmit, which is the TDX parameter, is associated with pin D1, pin 3. So we need to communicate our chip with a to communicate serially with a sensor. Then we need to look at pin 2 and pin 3 in parameters receive and transmit. So let's see what we need to do for communications to happen. Let's start physically. We need to connect the TX pin to the RX pin of your computer or your transmitter. Basically, your transmit on your microcontroller gets connected to the receive in your sensor or in the computer or laptop. Next, your receive pin is connected to the transmit pin of your computer sensors. So this pin would go to the transmit goes to the receive of the sensor of the computer. And then must have common grounds, and basically you have to be concerned with your grounds. Next, let's talk about the baud rate. So, for example, you can set up a baud rate of 9600 bits per second. Now, you cannot input that number directly into your microcontroller register. What you need to do is you need to calculate a parameter UBRR, and that's what you're going to enter into your register. Now this parameter is based on the bits that you want to input and also the microcontroller clock speed. So this is the formula. The UBRR register is equal to the microcontroller clock speed divided by 16 divided by the baud rate that you want to use and subtracted -1. So let's go through an example. So in our case, our clock is 16 million hertz, 16 millicycles per second. Let's assume we want to use a baud rate of 9600 bits per second. So then our UBRR register, which is the register where we have to put the input and controls the baud rate, is going to be 16 million divided by 16 divided by 9600 -1, and that gives you 103. Let's look at the frame format. That's the word that you're going to send out. Now, you define it using the user control and start register C. Typically we have 8 bits, no parity, and 1 stop bit. That would be our frame. And then finally, to be able to transmit and receive, we have to enable the transmitter and receiver, and that's in the control and start register B. So this shows you in a nutshell what is that you have to do top level to communicate serially. So you have to connect your transmitter to your receiver, receivers to transmitter, sensor computer. You need to be able to calculate your parameters to the correct, so you get the correct baud rate out. You need to set up the frame, and you need to enable your transmitters. So let's look a little bit more let's get a little bit deeper into the data format. Let's start with the frame formats. So an 8-bit is the standard in most modern communications. So it's usually 8 bits is what everybody uses. Next, 1 stop bit is the most common, which signifies the end of the frame. So this is what the frame would look. So you would have your start bit. Next, you would have your 8 data bits, and finally your stop bits. Now let's look at the baud rate. 9600 bytes per second is one of the most universally supported baud rate. So almost everybody uses 9600 bits per second. However, some of the sensors that need higher rate, they use 115,200 bits per second. Next, we have the baud register. It's important to understand what this register looks like. So that was the one that we calculated, the UBRR0H. So we have 2 registers where we have to put that information. We have the UBRR0 low, which is the 8-bit register which contains the low, first 8 low bits, and then we have the UBRR0H, which contains the high 4 bits. So we have a total of 12 bits to where we place the result of the calculations that we did with for the UBRR0. So here below shows you what this typical would look. You would shift your result by 8, and that's when it goes in your high bit, and then you just would put the whole first 8 bits into your low bits. So let's start talking about the framework. We'll review the data sheet, and next we'll prepare the framework. All the data that we need to put together our framework is going to be obtained from the data sheet. Now the data sheet is organized by functionality. So let's jump to the section 24, which is the universal synchronous asynchronous receiver transceiver. In this section we're going to jump to the register descriptions, which are the ones that we have to manipulate to get the desired behavior. Now we have here 6 registers, 1 data register, 3 control register, and 2 baud rate register. So let's go to the data register. Now this register is going to contain any data that we receive, and also we are going to, when we want to transmit data, we're going to place it in this register. Now the control register 0A contains all the flags which are going to give us an insight into the state of our transmission. Next we have 2 additional control registers, control register B and control register C. From these registers we're going to be able to control the transmission mode, the word side, stop bits, whether or not we want to use interrupts, and also we're going to be able to enable or disable our transmitters. And finally we have 2 baud register 0 register low and baud rate 0 register high. Now the value stored in these 2 registers are going to be calculated based on the baud rate we want to transmit and our processor speed. So these are 12 bits. The low rate, the low is just we can use the whole word, and the high we're going to be able to use the first 4 bits, and that makes our 12 bits that are going to define the baud rate. So with this, I think we have enough information to put together our framework. Okay, so let's go ahead and put together our framework. So the information on this table is the one that I got from the data sheet. And based on this information, I'm going to write my code that is the one that's going to define our framework. So this is the data. Next, again, I show these are the registers that we already talked about on the when we looked at the data sheet. So this is continue with the writing the code. So the important thing here is that we look at the data and we write the code. So finally, this is what our framework is going to look. The framework will be implemented as an include, and we're going to call it framework_UART. Now, the source code, like I mentioned, is basically I extracted what we have on the column that was named code. Now, to prevent any naming conflict with existing development environment, the parameter net have been modified with an X in the front. Like I was mentioned, this information, this thing that I prepared here, the framework, is already done by the environments, most of the environments. However, it's important that you understand where things come from. And also, as a side effect, we have created traceability to our source code back to the ATMEGA 328 datasheet. So we can look at our source code and see where it came from. So let's start with our first example program. So what we're going to do, we're going to have two microcontrollers hooked up seriously. So you have the transmit to the receive to the transmit. Now one of the microcontrollers is going to have a LED hooked up and a switch. The other one is just going to have an LED. Now what this program is going to do is when we press this button, then this controller is going to send a message to this other controller to turn on this LED. When this controller receives the turn on or turn on message, what it's going to do is going to reply with an acknowledgement. Now we press the button again, then this microcontroller is going to turn off the LED and send the acknowledgement. So let's look at the requirements for the what I call the controller. So I'll call this LED, this microcontroller, the controller, so we can differentiate one from the other. So when the switch is pressed, then transmit a light on message. So the light on message is going to be hex 0F. Now flicker the LED 8 times if the acknowledged message equal to 06 is received. Keep the LED on if no acknowledgement is received. So somebody pushes the button, we send the message to turn on the LED, a acknowledgement is received. If we get an acknowledgement, then we turn on and off this LED 8 times. If we don't get an acknowledgement, then we just turn on this LED and just leave it on. If the switch is pressed again, transmit the light off message, which is going to be equal to F0. Flicker the LED 8 times if acknowledged equal to 06 is received, or keep the LED on if no acknowledgement. So basically, every time you push this button, you turn it on or off the LED on this other microcontroller. Now, the transmission parameters, it's important that both match it. We're going to use 9600 baud rate. Our frame is going to be a 8-bit, which will have 2 stop bits and a add parity. So now let's look at what I've called the subordinate, just to differentiate. So this is going to be the controller and this is going to be the subordinate. If a light on message equal to 0F is received, then turn on the LED and reply with a acknowledged message equal to 06. If the light off message equal to F0 is received, then turn off the LED and reply with an acknowledged message 06. Transmission parameters are going to be rate 9600, 8 data bits, 2 stop bits, and 1 parity, and add parity. Sorry. Okay, so let's look first at the controller software. This is the code for the controller. So let's start analyzing the code by looking at the header. Here at the header we have a parameter called the baud. That's going to contain the actual baud rate that we're going to use for our transmission. In this case is 9600. Next we have a parameter which is my UBRR. This is the calculation which is the value that's going to go into the UBRR register. Now we do this here because if in the future we want to change the baud rate, then we just have to come to this to change it in this header, and the rest of the program would remain the same. Here we have a parameter which is acknowledgement, which is going to be the value 06 hex. Next we have the on command, which is going to be 0f, and then followed by the off command, which is going to be F0. Now let's look at the init port routine. In this program we're going to have an LED, hence we need to set the port B1 to output. We're also going to have a switch, so we need to set the port B2 to input. And as usual, every time we use a switch, we need to have a pull-up resistor. Now let's look at the init UART routine. To set up the baud rate, we basically have 12 bits, which are contained in 2 registers, the BRR0 high and the BRR0 low. The BRR0 low contains the first 8 bits, and the BRR0 high contains the rest of the bits. You can see how these 2 lines of code implement that. Next, we have to enable our receiver and transmitter. That's what this line of code is doing. We also have to set up, we have decided to use a format of 8 bits for our frame, and that's accomplished by these 3 lines of code. Next, we're going to be communicating asynchronous, normal mode, parity 0, and that's what these 4 lines of codes are doing. We're going to enable the add parity. That's what this line of code does. And then we're going to enable 2 stop bits. Next we have the UART transmitter. The idea here is that first we have to wait until the buffer is empty. Once the buffer is empty, then we can place our data to be transmitted. So that's what this while is doing. It just basically checks this the flag, the empty transmit buffer flag, and when that flag becomes true, then we jump out of the while loop and we place our data into the buffer. Next, let's look at the UART receive routine. It's very similar to the transmit. So what we do here is we wait until the receive buffer is empty, which that's what this while is doing by looking at this register and then at this particular flag. When the flag gets set, then we know that the data has been received, and then we can place the data into the data buffer, into data parameter, I should say, and then we return the data. So one of the 2 things that we have to be careful with these while loops is that these while loops have the potential to get into an infinite loop. So we really should add some code to make sure that this times out. I don't do it here because I don't want to add more code and complications to this program. So let's continue. We have the next routine is going to be LED blink routine. What this routine does is waits to receive data. It's going to come from the subordinate. So we just wait for the data from the subordinate, and once we get the data, we check if the data is an acknowledgement or not. If it's an acknowledgement, then we turn on and off the light 8 times. If it's not the acknowledgement, then we turn on the LED and just leave it on. So let's get to the main program. In the main program, we're going to initialize the ports and we're going to initialize the UART. Then we have 3 parameters here. One is going to be called the new input. The next one is going to be the button all input. And finally, we're going to have the LED state, which gets initialized to LED is off. So let's look at the while loop. The first thing we have is a delay of 80 microseconds. The issue is here that when you push the button, you press the button, you're going to have a lot of bouncing. So you have to ignore that. So that's why I put this 80 microseconds delay. Now this delay I figure it out by experimentation. Next you have the new input, button new input. So what this is going to contain is the state of the button pin B2. So it is going to be a 1 or a 0. So the first thing we ask is, hey, is the new input equal to 0? And if that's true, then we ask, hey, is the old input equal to 1? If the answer is 0, that means that the button got pressed. So why am I saying this? So if the old input was a 1, that means the button was not pushed. And then if the new input is 0, that means that the state went from 1 to 0, which means that the button got pushed. Now the first time we come in here into this if statement, the LED is going to be off, because that's how we initialized it. So then we need to turn it on. So what we do is we send through the UART transmitter the on command. Then we go to the LED blink. The idea here is that we send the on command, and then we're going to wait for the reply from the subordinate, and if it's the acknowledgement, then we turn on and off the LED 8 times, or else we just turn it on and leave it on. Next here we change the state of the LED, because now the LED is on. The next time we come in, the LED state is going to be on. So we're going to jump to this else statement. So we have to send the request to turn it off. So we're going to transmit the X off. I should say the command to turn it off. Then we're going to LED blink, which is going to check if we get or not the acknowledgement. And then we change the state of the LED to equal LED off. And finally, every time we get into this loop, the last thing we do is we set the button all input equal to the button new input. So that concludes the explanation of the analysis of the controller software. And next, let's go to the subordinate software. Okay, so let's go to the subordinate software. This is the subordinate software. Let's start our analysis from our header. As before, we've defined a parameter, the baud, which represents the value of the baud rate that we're going to use for our transmission. Next, we have my UBRR. That's the value that we're going to calculate, which will be loaded into the BRR, I should say, register. As before we do this, if for some reason we need to change the baud rate, then we just have to come here to the header and we don't have to change the rest. Now we have the value of the acknowledgement, ACK, which is going to be hex 06. We have the on command, which is 0F, and the off command, which is F0, and a couple of other two parameters. So let's look at the init port. We have one LED hooked up to port B1, therefore we need to set port B1 to output. Next we have the initializing the interrupt. In this for this program we're going to use an interrupt to let us know that data has arrived, instead of having to do the while loop waiting for the flag to be set. So in this case the flag is going to be set, but that's going to trigger the interrupt once the receiving buffer is complete. And then here we have the global enabling of the interrupt. Next we go to the init UART routine. This is going to match the routine we developed for the controller. So we have the baud rate here, the low that contains the first 8 bits, and we have the BRR 0 high, which contains the last 4 bits, which are the 12 bits required. Next, we have to enable the receiver and transmitter. We've decided to use a frame format of 8-bit, which matches the controller. We always have to match the controller if we want to have a transmission between these two controllers. Here we have set to normal mode. I forgot the asynchronous UART transmission. Normal mode. Parity is going to be odd, and we'll use 2 stop bits I showed here. Now let's go to the UART transmitter, which is similar to what we did with the controller. So the idea here is that we're going to wait until the flag is set, stating that the buffer is empty so we can load it. So this is what this while loop is doing, checking for the flag, and if the flag is set, then we jump to the statement, which is the UDR0 equal to data. We're storing the data into the transmitter buffer. Now let's move into the main program. So what the main program does is init the ports, initialize the UART, initialize the interrupt, and that's all the main program is doing. Next we have our interface service routine. Now this routine is going to be triggered every time the receiving buffer is full. So in this case, the first thing we do is we load the data that has just arrived into the data in parameter. Next, we ask if the data is commanding us to turn on the LED, and if that's true, then first thing we do is we transmit the acknowledgement, letting the controller we got the message and we're going to turn on the LED or off. Next, in this case, we will be turning on the LED. and then we continue to the while loop. The next time we go into the interrupt service routine, what's going to happen is if the data in is going to be not equal to on, so that means it's going to be equal to off. So in this case, first thing we do, we acknowledge that we got the message, and then we turn off the LED. So this, we're going to go to the while, and just every time a message comes, we'll get interrupted. So that concludes the analysis of the subordinate routine. Okay, so now let's go to another example, the second example. So what we are going to do in this case is we're going to connect our controller to a laptop, and we'll have, of course, a USB serial adapter. What we're going to do in this case is the controller is going to send information to be displayed on the laptop, which is going to be a menu. And this menu is going to tell the user to input a number between 1 and 9. Once the user puts in the number, then the controller is going to get that number and is going to turn on and off this LED depending on the number that was transmitted. So if the user puts in a 3, then this LED is going to come on and off 3 times. So again, this is going to be the controller. Transmit to the computer following text. Enter a number between 1 and 9. That's the menu that is going to be displayed on the laptop. Wait for the computer terminal to reply. Based on the reply from the computer terminal, blink the LED between 1 and 9. So the menu says enter a number between 1 and 9, and then we wait for the user to put in that number, and we figure out based on that how many times we have to turn on and off our LED. After each transmission to the computer terminal, clear the screen and set the cursor to position 0, 0. So once the user has put its input, what you want to do is clear everything and display the menu again. Now our transmission parameters are going to be a baud rate of 9600. The data is going to be 8-bit. We're going to have 2 stop bits and add parity. So let's look at the subordinate. The computer terminal will display the text sent by the microcontroller. So this laptop, it displays the menu, but really it's not doing anything, just doing whatever the microcontroller wants. User will enter a number between 1 and 9. The computer terminal will transmit the number to the microcontroller. The computer terminal will wait for further instructions. And then again, we have our serial parameters, the baud rate 9600, which basically matches the controller. 8 data bit, 2 stop bits, and parity odd. Now the one thing I just wanted to notice that the laptop will have the Terra terminal, and that's an application, so the user will open the Terra term application and then set up the parameters like I showed in the first example, which have to match these parameters. So let's look at the code. This is the controller software. Let's start our analysis from the header. So we have a parameter called baud, which contains the value of the baud rate we're going to use for our transmissions, same as before. Now this is the MyUBBU-BRR, which contains the value which is going to go into the UBRR register. As before, we do that in case we need to change the baud rate. We would just come here and we don't have to worry about anything else. Let's go to our init routine. We have one LED which we're going to turn on and off as many times as we are commanded to do. So we need to set this to output. Next, we're going to use, we go to the init interrupt routine. We are going to use this routine to enable the interrupts for the receive, meaning that every time we receive a message from the subordinate, an interrupt will be triggered and we can get the data. Next, we have our init UART. This is going to match the receiver, or I should say it's going to match the subordinate. So we have our baud rate, which is going to be 9600, and here we have these two registers which are going to accomplish that. Next, we have to enable the receiver and transmitter. We've decided to use an 8-bit format frame, so that's what this three statement will do. We're going to use a synchronous transmissions. It's going to be in normal mode, add parity, and 2 stop bits. So these are these parameters. Yes, sets all the transmission parameters which have to match what we're going to use in our subordinate, which is going to be the teraterm. Now here we have the UART transmitter. What we do here, as we did before, is we have this while loop and we just wait for the buffer flag, buffer empty flag to be set, which means that we can load our data. And with this statement, we load the data into our transmission buffer. Now, the next routine, which is clear screen, we're going to use a command to clear the screen and a command to set the cursor at row 0 and column 0. So what we want to do is in the serial terminal that is on the laptop, we want to send a command to clear the screen and put the cursor in the location 00, so we can write everything from the left corner tab, from the top left corner. And these are just the typical commands that do that. You can look at your serial commands and you'll find these values. So we have to send one ASCII character at a time, so that's why we have this loop, which is the load the clear. And then here we have to send again one ASCII character at a time. So we have the cursor, which is a pointer to this value, and what we do is we send one at a time. Now let's go to our main program. We're going to initialize the ports, initialize the UART, initialize the interrupts. Now we're going to set a parameter called blink, which is going to contain a string which says enter a number between 1 and 9 column. And then we're going to have another parameter called cursor input location. So we're going to command the cursor to go to a particular location. And then we're going to have, so that's the two commands that we have. So let's start the program. It starts with clear the screen. You clear completely the screen, and next you're going to transmit the enter a number between 1 and 9 here. And after that, you do that, then you're going to place the cursor in the correct location so the user can input the number, and that's cursor input location. So let's see what this would look like. So this is the subordinate. This is the what it would look once it reads the inputs from the controller. So you would have, so first it cleared the screen, then it wrote enter a number between 1 and 9. So first thing with this, we need to put the cursor in location 0, 0. Next we have to write enter a number between 1 and 9 column, and then we have to place the cursor in this location. So that's what's happening here. We clear the screen, we write the enter between 1 and 9, and then we place the cursor as I showed you. So then you get into the infinite loop. Now this interrupt service routine is going to be triggered every time we get an input from the controller. So when we get an input from the controller, what we're going to do is the following. We're going to clear the screen, and we're going to put the enter a number between 1 and 9 column statement for the user to know what to do next. So this is what this for loop does. It puts the enter a number between 1 and 9. Then next we're going to get the data that the user sent. So that's this buffer will load data in with the contents of the buffer UDR0. Now what we do here, we ask, hey, is the data between ASCII 0 and 9? What I'm saying here is the data between 30x and 39 hex. So 30 hex and 39 hex. That would be the value for ASCII 0 and ASCII 9. And if the answer is yes, that means that the subordinate has sent us a number between 1 and 9, indicating how many times it wants us to flicker the light. So to figure out what number it is, we take the data that we got from the user that may be between 0 and I think it's between 1 and 9. I'm sorry, between 1 and 9. So then we subtract 30 minus the number we got from the user, and that gives us how many times we have to flip the light on and off. So you can see here, if it sends a 1, then that would be 30 minus 31 minus 30 would be 1. If it's a 2, 32. So that's what we do here. So we calculate data in by subtracting the ASCII value from the data obtained from the user. And next we go through our loop, which turns on the LED, waits half a second, turns off the LED, waits half a second, and does that a number of times as commanded by the subordinate. Next, when we're done, we set the data in to 0 to clear the buffer, and then the program would jump to the while loop again. And let's look at the subordinate one more time. So this is the Terra terminal that we configure to the correct value so it could communicate with the controller, microcontroller. And this shows the enter a number of between 1 and 9, and then the cursor where the user is going to put its input. So That concludes the analysis of the this second example for the controller, and also I showed you what the subordinate would look like. Okay, so this is the end of the presentation. So today I gave you a background on the USART. We developed a framework, and finally we went through two representative examples. So I hope you've enjoyed these presentations, and thank you for taking the time to listen to me.